Hello everyone, I'm Manuel. I'm a PhD student at the University of Toronto in Canada, and I've been working on the Rust compiler for like the last 3 or 4 years or so. My goal is mainly to make Rust more accessible, more usable for generally scientific computing, machine learning, high performance computing, and all of these applications in that field. So one module which I've been adding to the Rust compiler specifically over the last year is called standard autodiff, which enables automatic differentiation, like we know it from a couple of other languages, like Python, and we now have it in the Rust compiler as well. So for those of you who are new to automatic differentiation, the idea is we just want to compute gradients and derivatives as we've been doing it in like analysis courses in high school. So there are a couple of ways to do that in software, and a pretty simple one is maybe find a difference. So if we don't know like how to optimize a function, then we can just evaluate it in a couple of points and see how the function changes. But that's a pretty expensive solution, especially for machine learning applications where we have billions of parameters. We can't really evaluate a neural network billions of times. That's too expensive, and it's also not really accurate as well. So if we just want to compute gradients, like can the Rust compiler do that for us? And yeah, like one example is, for example, if we have a simple function like x times x, just square a number, then the first derivative of that is 2 times x. And now we want Rust to do that for us. We use these type of like toolings, like automatic differentiation, doing backpropagation of neural networks, as well as like just climate simulation or every larger numerical application where we want to tune a couple of parameters. So as I mentioned, I've been working on that for a couple of years. So the basic features are already upstream in Rust right now. You can see them in the Rust repository. We are mainly working on making them more usable, making them more robust, so you can actually start using them in your applications. And there are a couple of related features about which I'll talk towards the end as a small outlook, which are called GPUs offloading and vectorization, which are another few nice features which we want. And yeah, once everything is reliable enough, we'll enable it for nightly, because right now, if you want to use any of these features presented today, you're going to have to build your own Rust compiler. It's not that complicated, but it still takes a little bit of effort, especially on older hardware. So let's see. One of the latest improvements, luckily, have been from 2 students, which have been helping me out over the summer through the so-called Google Summer of Code project. The first one is Marcelo, who was under the Rust Foundation. The second one is Karen, who has been part of the LLVM Foundation, and they've been helping by rewriting how we use automatic differentiation in the Rust compiler. So first improvement is automatic differentiation is now properly integrated in the Rust compiler. Previously, it took me a couple of iterations to add it, and there were still some, let's call it hacky areas of it, which caused a couple of bugs. So he's been like just re-implementing our whole Rust front end, whereas Karen has been working with us on giving more information from the Rust compiler to our compiler backend, which is called LLVM. So LLVM does all the heavy lifting, the code optimization, all of that. And if the Rust compiler gives more information to LLVM, LLVM can do a better job at that. So he's been helping on that side. So first of all, I'll show how automatic differentiation nowadays works in the Rust compiler. And the idea is it's a simple macro. So you can add it to any function you want. You just write #autodiff, either forward or reverse, on top of your Rust function, and we're going to generate a new function for you. And the new function it's a normal Rust function. You can call it. You don't see all the magic happening under the hood. But if you look at the cargo expand command, then on the right side you can see what this macro is expanding to. So the first thing is we keep your original Rust function, which in our case just computes sign, but like it can be anything. It can be like do the inference for this neural network, run this climate simulation one step, do a numerical optimization. Can be whatever. And now the new function which we get is the cosine box function here, because the derivative of sine should be cosine. So if the compiler does everything correctly, that new function should also return the cosine of our function. Or, well, in the case of neural network, it would like do the backpropagation for us. And we can see the second function is a lot more complicated. It has a few extra parameters, like dx, which will then compute the cosine for us. But the really annoying thing for us is all of this random code which we don't really need in here. So the reason we have had it in the past is the Rust compiler does not really know how to compute gradients. The compiler backend LLVM does it for us. So we have to add the placeholder for that. And well, what we see here is that placeholder. The first one is just an unsafe assembly block. Assembly is something which compilers still don't really fully know how to optimize. So it's just there to prevent our compiler backend from deleting the function, because it does not fully know what's inside of the assembly block, and so it won't delete the function, because the function itself might be quite useless up until the point where we ask LLVM to generate the correct derivatives. So now we have a few more black box, and these are just because, again, the Rust compiler tries to be smart for us and tries to give good information to LLVM. So the first thing is, well, we call the original function inside of our placeholder function. That just links these two functions together. So as a compiler, we know, well, one function computes the derivative of the other. We need that inside of the compiler. That's fine. The next one, the black box, these ones just uses our argument. It doesn't do anything with them. It just marks them. That's why we use the black box as used. So the Rust compiler will not use these, will not delete those arguments for us, which it would otherwise do. And the last black box call in this case is just, well, even if we're in the compiler, we cannot do black magic. We still have to pass the type checker, we still have to pass the borrow checker, all the things that a normal Rust user has to do, we as a compiler also have to follow them. And so the last line here is really just to make sure that this function signatures match. Because in this case, both functions return a float, so we just make sure that this function also returns a float. And again, all of that is just a placeholder. We're going to delete all of that code later and just compute gradient. So there's no reason for it to be there. And so that's what our summer student has been doing. And he introduced a proper autodiff intrinsic. So now all of these hacks are gone. A couple of bugs are gone. So the autodiff macro just works a lot more reliable. You can use it on more code now. And as you can see, the intrinsic is pretty simple. It takes the original function. Again, we need to know which two functions are coupled together, so we compute the correct derivatives. It keeps the name of the new function. If we had generic arguments, we'd pass them along here as well. And then it just passes the arguments which are needed to compute the gradients. So that's great. It also reduced the size of the Rust compiler by 700 lines of code. We simplified the parsing. We have less bugs, and yeah, some of them have already been closed. So what the second student over the summer has been working on is a bit more on the compiler backend side, because computing derivatives on the source code sounds a bit weird the first time, right? Because you normally compute derivatives and gradients for some math functions. And on the compiler, on the source code side, sometimes we lack a little bit of knowledge that we have on the math side. So if you look at, for example, this function f, all it does is really call memcopy, which means copy this number of bytes from one memory location to another. It's not really an inherently interesting function, but it's something we do a lot of times in the Rust compiler. Every time you call clone or copy, under the hood, that's a memcopy. And so computing the derivative for a memcopy, therefore, is just something very basic which just needs to work. And the interesting thing is now, if we look at this code, by the way, it's C, but the same would hold true in Rust. I just use C because it has these nice void pointers which lack any sensible information. So if we assume that this memcopy is called on some double values, then computing the derivative for that double would need us in the reverse pass to call one addition. If we had floats instead, well, one float is 4 bytes, so we copy 2 floats over. If we have an 8 here, then we'd call 2 additions. So the point is, based on what type we really have there, we compute different derivatives. And we might assume that in a normal Rust code, we always have this strong types. We are not Python, right? We have these type information. But that's not really true. When we lower Rust code to the LLVM backend, we try to make it as generic as possible. When possible, we try to elide a couple of information. For example, we represent a lot of Rust types as more or less I8 types. And in that case, well, the Enzyme autodiff backend does not really know what gradient to compute there. So what the student has been doing is help the compiler in that case out a little. And the reason why we care is twofold. First, if Enzyme doesn't know what types we have, the only valid thing is to abort the compilation. Because we would be guessing otherwise. We might compute the wrong gradient for you, and that's just quite hard to debug. So if you go to the Enzyme repository, which implements all the autodiff tooling and the logic, then you see a lot of these open issues like cannot deduce type of something. And we don't want these issues to show up in Rust, so that's why we lower all the good Rust information we have to LLVM. And the other one is I've been doing a little bit of benchmarking of automatic differentiation in Rust. And as you can see here, it was just a simple application of some ML model to chemistry workloads, since I'm supporting a chemistry group in Toronto. And you have some quadratic explosions here. We start with a compile time of 1 second, maybe 5, 10, that's all fine. But here it goes to 100 seconds, 1,000 seconds, and from there on it quickly becomes unusable. Which is because Enzyme tries to analyze the usages of your variables. So if you try to differentiate some code, and the Rust compiler or LLVM does not know which types you have, they try to look at every single byte, at every single element. So if you have a vector with 1,000 elements, the compiler is going to try to analyze 1,000 elements in your vector and figure out what type they have, which is extremely slow, so that quickly becomes quadratic and unusable. So the way to fix that, which we've been adding over the summer, was just pass all the information we have from Rust to LLVM. It looks kind of tricky. Still don't do that at home. So if we, for example, take a simple Rust struct, then we have our indices like offset 0, offset 4, offset 8, because they all are the same size, some floats, some integers, and well, that has to be represented on the compiler side. So we have a type tree, which just means we have a lot of types in there. In our struct, it's like the struct has internal types. It can be even recursive, like it can be nested types. That's all fine. And yeah, then we load that on the LLVM side. And on the LLVM side, we have a so-called metadata called enzyme type, which really just for each byte describes what the original Rust type was like. You shouldn't do that at home because as a Rust compiler, we are able to reorder your structs. So even if X, Y, and ID are in that order given in the Rust source code, maybe on the compiler side we decide it might be more efficient to have the integer first. So we might have the ID first. So as a Rust user, you should be a bit cautious if you try to really rely on the layout of structs, unless you represent them as C-like structs. But that's what we've been doing. And that should both fix the quadratic compile times, and it should fix the crashes where our autodiff tooling cannot deduce the type of a variable. So if any of you want to see more details, I've added the slides, links to the blog post to the PDF. And yes, so there are a few more improvements which I want to mention for users. The first one is, right now we have not the greatest compile time, but at least it works in the first approach. So we require you to use ATO equals fat, which just means take all this Rust source code which you have and more or less clump it into like a single binary, a single object file, a single LLVM module, which makes it very easy to process it, but it also means the compile times are going to be very bad because you lose all parallelism of the Rust compiler. Again, it's a temporary workaround, and now we automatically enable it for you. In the past, we, as a user, had to ask you to enable it by hand, or you would get the wrong results. So having it automatically is nice. The other improvement which we got over the summer is, well, in the past, you've been getting the wrong results if you used automatic differentiation in a library. So if you were the end user and you had it in your binary in your main.rs file or anywhere, then it worked totally fine. If you now create a library, like for example fair, like one of those Linux libraries, and upload it, and use autodiff in there and someone else uses you as a library, then you got the wrong results. So now you get a proper error for that. And the last one, we now have proper CI running. So that just means we should fix issues if they come up, regressions, all of that a little bit earlier. Okay, and so now I want to show a little bit of live demo. So that was based on an earlier course project which I had with two collaborators. Let me see which one. No. Okay, yes. So the live demo is based on Carpathy, who has been working a lot on machine learning applications. And he has a couple of projects where he has very simple implementations of large language models, like for example GPT-2, LLM.C, and that's one which I've been looking at. So we're going to move into the LLM.C folder, and wait. That's not great with the microphone in hand, sorry. Okay, yes. Yes, so the first one thing I want to demonstrate is his C code. So that all is a very simple case because as a side note, the autodiff tooling which I'm presenting works in other languages too. So we have C and Julia support. Obviously, I'm most interested in the Rust front end, but it works for more languages. So one thing we've been doing is we went through the source code of Carpathy and just deleted everything which had backward in the name. Because the way normal, like manual backpropagation works, you have a forward function, which does the machine learning inference. So if you have a trained neural network, all you want to do is like load those weights, do a couple of matrix multiplication, and you get a classification result or an object detection result, right? That's fine. But like if you actually want to train your model, then you need to do backpropagation, which just looks at like, you have a couple of data sets, a test set, and look how good are your weights on that test set, and based on the error you get, you update your weights. So we delete all of that backward code, which you can see here on the left side. On the right side, it's just completely gone. And the good thing is, well, we don't need it anymore because automatic differentiation is going to generate the code for us. And the second change in that source file was, well, the original Carpathy implementation for LLMs was just calling GPT-2 forward, 0 gradient, and GPT-2 backwards, after which it had the gradients available to call the update method and adjust our weights, so in the next iteration we're going to get better results. All of that's gone on the right side, because now we have automatic differentiation, which is like all fancy pretty, so well, the code is all gone. What we do instead is we call Enzyme autodiff, which again, Enzyme is just the name of the plugin which does automatic differentiation for us. And we see the new function, well, we just give it the forward function, the inference, if you want so, and we pass a few extra parameters which now suddenly have all the gradients in them. So that's great, but at the end of the day, we don't really care about C code, right? So what we've been doing is, documents, sorry, that's the wrong one. So, yes. So I have a single C file here now, which is, again, the whole implementation of Carpathy's LLM.c. I just simplified it to a single file because it included a couple of different files. I just merged all of these files into a single code base. And now, interestingly enough, we just had C2Rust on the last presentation. I can post it into the C2Rust website. Click on, oh, I think, well, the website seems a bit large and too large on my demo, but it's fine because I already downloaded the Rust version of that code. So you have to trust me now that this is the same code. Okay, so now we have the Rust version of LLM.c of Carpathy's machine learning implementation, and a couple of things which I've been changing in that file is pretty much only 3 lines. So we have a new feature called autodiff. That's the one I've been working on. We also use that new feature, so we say use standard autodiff star. And the last one, if we go down a little, so exactly. So what we do now is we call our new autodiff macro, which we have now as part of the Rust compiler. We tell it a couple of information about that function, because GPT-2 forward does a lot of things. It has a lot of input parameters, and we don't really want to compute gradients with respect to our parameters, right? There's no way, we cannot optimize the training set. We can only optimize the weights. So we can then tell that to our compiler and say, hey, just like take the model, which is the first argument duplicated, and like give us a new model which just contains the gradients. And then we're going to use the new model to train our network. That's fine. And the other thing is, we are now calling the GPT-2 AD backward method, which just forward model, so the inference, the training, the updating, and all of that. And in the second call, we do call GPT-2 update, which then improves our trainings. So the way it works now is, the whole compiler invocation is still a bit more verbose than your normal cargo compiler invocation because it's a very experimental feature. The first thing you can see is I call cargo plus Enzyme. Enzyme is a special toolchain, like you might know stable or nightly or beta. That's just one more toolchain which I've installed locally because we don't distribute autodiff yet on nightly. Then I also have Rust flags. Because it's an experimental feature, we really want to make sure that people are aware that they use an experimental feature, so we force them to do a user nightly -z flag called autodiff equals enable. And with that all together, we get a new compiler invocation. I'm running a bit short on time, so I'm going to skip some of the compilation parts now, but what you see. Okay, so that's the Rust version of our LLM. And we can see like it's loading a couple of parameters. And yes, therefore, we're going to wait a few seconds till it starts to train. And well, just give it a little. Again, this is like fully unoptimized code, so we got it from the C2Rust project, which worked great for like a couple of other things we tried as well. But the downside is, this is the Rust code which you get is completely unsafe. It uses raw pointers, it doesn't use any Rust references, and that's going to cause us a couple of issues, which we'll see in a second. Because right now we are just before calling automatic differentiation, and now we are just waiting for it. I can, as a little spoiler. So I've been running that in the past successfully on a server which had 500 gigabytes of RAM. My laptop does not have 500 gigabytes of RAM, so in a second we're going to see an issue here. Yep, everything's red, and our program got killed. Okay, let's go back to our demonstration, because that's what I wanted to see. Okay, so a couple of things on why that doesn't work fully yet. First thing is, if we look again at the C example, we got the Rust code from C, right? So it's completely unsafe, it uses raw pointers. It's not great. I've mentioned before that raw pointers lack type information, which we've been working on for the summer, but they also lack alias information. So the question is like, do two pointers point to the same memory location? Super critical for automatic differentiation, and that's why our performance is pretty bad. So I'm going to go quickly over these benchmarks. The first one is an LLVM, so some machine learning benchmarks. I have a few other ones as well. And you can see in dark red, idiomatic Rust is usually pretty good. Like the higher the better on these benchmarks. And then unsafe Rust, which you see in orange, is usually, like in some of them it's doing okay, and some is like almost 10 times slower. So unsafe Rust can be really bad for automatic differentiation, just because raw pointers really lack a lot of information which we need in the compiler. Yes, I'll speed up a little bit. The other thing which I wanted to mention is for machine learning workloads, you don't really do like all these things which Carpety did by hand, right? You normally don't do that, like matrix multiplications and all of that. There are good libraries for that. They are called BLAS routines, for example, QBLAS on the NVIDIA GPUs or OpenBLAS on CPUs. And now the interesting thing is we've been also doing some benchmarking. So if you don't take Carpety's implementation, but like a proper one, which does call those routines, we've seen some huge speed up, like 64 or so. And that's just because if you use high-level routines, we have a bit of a better understanding on how those works. So that's another reason why I probably just ran out of memory. And there are a few more optimization which we can do for that in the future, but I'll talk about that another time. And yeah, so we have an outlook on what we have been implementing in the past, what's not yet fully available. The first one is called batching. You know that especially if you train neural networks, usually you don't pass like one image to the network to train it on one image. You pass 8 images or 16 images, or like a larger batch at least, to train all of those at once, so you get a better parallelization, you get better GPU usage and all of that. So that's a feature which we have partly working in the Rust compiler, should be coming soon. And the other bit trickier project, which I've been working on this summer myself, is called standard offload. So we hope that in the future you'd be able to execute almost any Rust code on the GPU. You can already do that in other languages like C++ and Fortran. They have OpenMP support, and there's technically no real reason why we shouldn't use all those libraries from other languages and also expose them in Rust. So I have a prototype of the Rust compiler where you can already take simple Rust functions without any extras and just call them like that, and they run on the GPU suddenly. There are a few more projects, but the benefit of the one I've been working on is we use safe and idiomatic Rust, because as we've seen on the previous slides, right, if you use unsafe Rust and raw pointers, you lose a lot of the benefits which we have in Rust. So yeah, the hope is that even things like printline I/O might work in the future on the GPU, and that should make it a lot easier to just write HPC or machine learning applications in pure Rust. So yeah, please let me know if anyone has any questions, or if I should go into more details anywhere.